Alrighty, well, it's 12:05 Eastern, so I'll go ahead and get started. We're going to start with a very basic overview of what the heck is an ISA, or an instruction set architecture. So when you are doing computer programming, there are layers to how a application that you use, say PowerPoint, is in how PowerPoint interacts with the hardware on your computer. At the very top level, you have the programming language, which is how people create applications. Directly beneath that, you have assembly language, which is machine instruction. It's more basic, and it is specifically telling the hardware what to do, rather than just being like, if this is true, then do this. Instead, it's saying, check the condition of this value and this value. If that's true, go to this next instruction. So it's the more complicated. And the way that most applications work is that the upper level language gets converted into machine language when you build the application and run it. And then that allows the CPU and any other hardware in your computer able to interpret that machine instruction and perform the proper operations. Now, machine instruction has to follow a specific set of instruction sets, which is where instruction set architecture comes in. It is the architecture that says, hey, these are the types of instructions that you can use for this type of CPU, which RISC-V is one of those said instruction set architectures, and the RISC-V3 processor is a processor that uses RISC-V. So, RISC-V. This is a reduced instruction set computer, version 5. It is an instruction set architecture. What the reduced instruction set part means is that every instruction is executed in a single clock cycle, which is really, really fast. On the contrary, there are also CISC machines, complex instruction set computers, which allow a single instruction to take multiple cycles of the CPU to execute an instruction. Now, RISC-V uses two different types of sets of instructions for you when you are building a CPU. The first is the base set. You select one of 4 base sets. Each base set provides a set of instructions, which is the minimum requirement for the computer to run. Then you can add extensions to it, which are just small sets of a few instructions that provide additional support, such as support for multiplication and division, support for floating point number operations, just working with decimals and such. But those are not part of the base sets. So RV32I is one of the base sets for RISC-V, and this is the 32-bit integer instruction set architecture. It means it works for 32-bit machines, and it is integer addition and subtraction, and that is along with standard control operations and such. All you really have is the additional integer operations, and that's all this instruction set contains. So memory access, how do you get information from your computer's memory and load it into the CPU so the CPU can perform an operation on it? And that occurs by using the load store architecture here. So there is a load command and there's a store command. The load command takes an item from memory and places it into the CPU, and the store takes a value from the CPU and stores it back into memory. Now there's a set of 32 dynamic registers in RV32I, and unlike other types of machines where they have specific registers for specific things, such as a register for a return address, a register for a stack pointer, a register for alternate links and such. The RV32I is just they're all dynamic. While there is standard convention of using the first register as a return address by using the second register as a stack pointer, there's no hard-coded use for this, so that can be changed depending on how the instruction set works, or how the programmer uses the instruction set. Now, the 30-second the 30-second register is a program counter, and that holds the value of the next instruction for the CPU to execute. So this is an example of the instruction format for RV32I. You can see there's 4 types here. You have R-type, I-type, S-type, and U-type. And to write down these instructions simply, on the right side here, through bits 0 through 6, you have the opcode, and that tells the machine, hey, this is the type of instruction that I want to execute. The RD column is the return register, so this is where the result of an operation will be stored. The funct3 value is essentially an extension to the opcode, and it states what specific action for that opcode do I want to operate. RS1 and RS2 are parameter registers, so they are registers that will hold values to operate on. So if you had add, which we'll cover just shortly, you'll see the first value would be an RS1 and the second value is RS2. Function 7 is, again, additional instructions on what exactly type of operation are you performing. And then we have immediate values, which is essentially hard-coded values in the instruction. So instead of doing register 1 holds 5 and register 2 holds 7, you would do register 1 holds 5, and then the immediate is a hard-coded value of 7. So speaking on immediates, there are some alternate types here. B is an alternate of S-type, J is an alternate of U-type. And the only thing that changes here is how the immediate values are read, where in B, it's the 12-bit field that's used to encode branch offsets in multiples of 12, and I'll cover branching shortly. While J just changes how the immediate is read for the U-type. It's going to be shifted 20 bits to the left, whereas the J-type is only going to shift 1 bit to the left, and it's going to be sign extended for the rest of the 31 bits. So, some example instructions. We have our mathematics here, which is type R, and our conditional jump here, which is type B. Now, as you can see with the type R, you'll see that there is the funct3 value here has a list of values, different types of instructions you can use for the opcode. You've got add, subtract, you've got your shift operations here, which just essentially move the value left or right because they're binary values. You have AND, OR, and XOR, and these are Boolean logic operations on 2 values. And then you've got less than and less than unsigned, and that is important because when you're doing binary values, the sign bit is the most significant digit, and it's not actually a part of the value. So you have to be able to determine if is it a signed or is it an unsigned value. And as I was mentioning with the RS1 and RS2 registers, as you can see here, add will take the first register, the value in the first register, and the value in the second register, add them together, and place them into the designated destination register. Then we have the conditional jump, which we take a condition, say equal, not equal, less than, greater than, or greater than or equal to, as is the case for this last value here. And we compare the first register and the second register, these 2 values, and it will take the branch. Essentially, it means it will go to the position that the branch designates if the condition is met. So if it is equal to or not equal to, then it will take the branch. And then the immediate value here provides an offset to the program counter of where to travel to within the list of instructions. With that said, extension M is the standard integer multiplication and division extension. It handles x length by x length computations, where x length is the bit size of a space memory. So if it's a 32-bit machine, it would be 32-bit by 32-bit operations. If it's a 64-bit machine, it would be 64 by 64-bit operations. There are two sets of instructions for extension M. There is no other instructions, only these 7, and they handle multiplication and division as said. Now with multiplication, because of the way that computers operate, you only have a specific amount of space inside of a register to store a value. So multiplication, the MUL command, will take only the lower 32 bits of the result, while you have to use MULH to take the upper 32 bits of the result. And then you would have to combine those values and save those values separately within memory. And that is something that's handled by the CPU design, because you can't do the full calculation and save the value with multiplication on a CPU, because it doesn't have that type of space. It has physical restrictions on the types of operations it can perform. Same thing with division, except the divide will operate properly, but if you want the remainder values, you have to do a separate operation for remainders. So, RISC-V3, this is a processor that was designed for a research project, and it uses the RISC instruction set architecture. It uses a redundant number system for every single operation on the CPU. Usually, CPUs will just use standard binary values, where if you just do a binary to base 10 or standard numerical system conversion, it would work properly and be equal. Redundant number systems are different because they take 2 bits per binary digit to determine the value of a binary digit. There's 2 types here, a binary signed digit and binary stored carry. Binary signed digits have a value of either -1, 0, or +1, and binary stored carry has a value of 0, +1, or +2. Now, the reason why this is beneficial to the CPU and circuit design that they chose to do is because standard addition operations within a CPU will compute 4 bits at a time, and they will pass a carry value forward, and then they'll do the next 4 bits, and then they'll pass a carry value, and then the next 4 bits. For computations that are 32-bit long, that takes time. With a redundant number system, because the fact that the values can have multiple representations for the same base 10 value, the only needed carry operation is a single carry for the entire number. So instead of doing 4 carrying, it just does the entire number at once, and boom, you have the resulting value for your add operation. And I say specifically add operation because computers do not do subtraction. They just turn a value negative and then add the 2 together if needed. Sorry, when doing subtraction, they just turn the second value negative and add them together. So it's always going to be addition within a CPU. Now, for benefits and detriments to the actual speed of executing instructions of the CPU in general, for memory access, so your load and store commands, it's dependent on what type of memory system you're using. For addition and other arithmetic, it is much faster than a standard CPU because the values are extremely computable. But for branch instructions and other instructions that require a specific point in memory to be accessed, then this slows down the CPU because they have to take the RNS value and convert it back to a standard binary representation, and then it can be used. All figures for this presentation can be found at the RISC-V Unprivileged Instruction Set Architecture Specification. They can be downloaded from their website at risc5.org. Thank you for watching.